Hello everyone. Let me just take a sip of the pepper real quick. Okay, so now that I've taken a sip of the pepper, let's begin. So last time I showed you guys the diode transistor logic gates, and so this time I'm going to show you something that they can evolve into, or what you can use them for. Something along those lines. Just gotta import it from text real quick. Um, all right, everyone. So here you'll see that we have our different types of latches and flip-flops. And so we're just going to get right into it. Oh, so here we have the most basic, which is the SR latch, right? And so what does this do? Well, all it does is flip between um, Q and Q naught and flip between the outputs. Obviously, with our SR latch, we have two inputs, and so it's our job to ensure that both inputs aren't the same at the same time. Otherwise, you get undefined states. This would be one. It doesn't switch. Or this one where they're both high, that's not supposed to be happening. So, that's the problem with the SR latch. But yeah, you see it just flips back and forth between low and high. And if we were to label this, which I didn't label it, like a fool, this would be the reset pin. And this would be the set pin. And then obviously over here we have Q and Q naught, right? I'll label that just for convenience. There you go, Q and then Q naught. All right, that's what your SR latch should look like. Obviously, the name set reset latch should make sense. And I built these from the component level, so once again, you can still see, what it would actually look like at the most basic level. And I did label the gates so you can see which ones was. So this is one using two NAND gates. You can also use two NOR gates to make an SR latch. Of course, I showed you in the other video how the DTL NOR is like two NOT gates put together. So in total, we would have four transistors, and that's a lot more than we want. So, extra stuff. So here we're going to move on to the D latch. And so what does the D latch do different than, well, the SR latch? Well, one thing it does different is that the input, as you can see, has been tied together to just one pin, which is the D, right? So we're playing with the D for the D latch, and we have an inverter. And so this ensures that the signal is high here, and so it enters into this part of the circuit as a high, and when it travels down here, it enters into the NOT gate or the inverter, and then it inverts, and then it's not high here. And so that ensures that we never have the invalid state that we can end up with in the just the regular old SR latch. And so what happens is we can flip back and forth after playing with the D input, and you can see high, low for the Q and Q naught output. So this is actually the SR latch, right here. And so what this extra bit does is that's controlled by the enable. And what this allows us to do is it allows us to lock in the data. So let's say I want the Q to be high. So what we do is we bring this to ground. And now if I were to try to play with the D and change the outputs, nothing happens because we've now locked the data to staying high. And this is actually very important for what? That's right, memory. We can use this for memory. Not this in its current form, right? You could try it, but it's level sensitive, and that would be a strange way. With handling memory, you would have to do a lot of special things to do it this way. And so now we move on to the next type of well, it's not really latch anymore. We're actually into the flip-flop territory. Here we have our D flip-flop, and this is in a master-slave configuration. So we have our slave D latch and our master D latch, and this allows us to now control it through a clock, so it's edge triggered as opposed to being level sensitive. So it maintains all the same ideas that we had before. I've also actually came and added a asynchronous reset, which you most often see if you were to buy those D-latch ICs. You'll see maybe 8 pins, 6 pins, something like that. I think it's 8. And you get like reset, you have a pre, sometimes a load, whatever. And so here you can see it triggers on the edge pulse. And so, it's high right now. So if we were to go over to the asynchronous reset, oh no, it doesn't go high anymore, even though our D input's high. And that's important for, you know, reasons, I suppose. Now, if we were to go from the D flip-flop, which is, you know, just a clock, it can now just be controlled by a clock, right? You can also actually add a, you know how this allows us to latch and enable? And you can actually make a D flip-flop latch, like the D latch, because, you know, by adding just some extra circuitry to the front, you know, I think it's like a 2-to-1 multiplexer and easy. And then you can lock in data as well, just like your D latch. And so the other type of flip-flop we have here is the JK flip-flop. And this one is pretty cool. I have my reset turned on, so let's turn that off. But when J and K are high in the D flip or the JK flip flop, something interesting happens. It doesn't go to an invalid state. Instead, it toggles the outputs, right? There's another type of flip flop called the toggle flip flop, which is just a JK flip flop, where you tie the inputs together, right? So I'm pretty sure. Like I said last time, we can just look that up to make sure I'm not making up some bullshit. Let's see, the T flip flop. Go to images and yeah, you basically just tie the inputs of a JK flip-flop together. It seems to be, yeah, here it is. We trust build electronic circuits, so yeah, essentially the same thing. So we're not going to talk about it, who cares? JK flip-flop, right? So we can also set just one to be high, so J, so our output is high. And if we were to flip this to K, now it should make the output here, it's for Q not output high, and the output for Q low. And of course we can also reset it, so wait for it to get high again, and here we go, it resets and it works. And all sorts of cool stuff, and there you go, that's basically your, these are your basic latches and flip-flops, and that's it's pretty cool, I think.